Nothing to say.
Good morning, ladies and gentlemen, colleagues. I'm Suresh Surushan, the president of the hydrology section. It's my distinct pleasure to introduce the 1999 Langbein lecturer for this year. Is our colleague John Bredehoeft. I don't know, John, if John needs really much of an introduction. He's internationally recognized an eminent senior colleague of ours from the field of hydrology and water resources. And I don't know, are there any people here who don't know John Bredehoeft? So with that, I will try to cut my introduction short so we can get to the lecture, given that we have a pretty much full day. After this, we have the hydrology business luncheon, which will follow. So I'll try to pretty much summarize John's contributions in geophysical aspects of hydrology. John has, over the years, played a major role in studying the role of fluid in geological processes, in terms of also looking at the interface between fluid flow and seismicity, well test analysis, and computer modeling of groundwaters, analysis of groundwater flow on regional scales, radioactive waste disposal. He's played a major role in trying to provide understanding to that issue, and water use and water management issues. And in terms of his administrative role, he played a major role within the U.S. Geological Survey's Water Resources Division. John served as for several years as the chief of the National Research Program in Menlo Park, and through that process, of course, he's been involved with a number of younger colleagues through the Stanford University and other universities. So he has provided much needed guidance to the younger generation. Very active professionally in various societies, including GSA and of course our own AGU. He has received the Robert E. Horton Medal of the AGU a few years ago. He has been a member of the National Academy of Engineering since 1994. And I'm pleased to introduce him, and today is going to talk to us about the use of groundwater models, period. John, I guess they've already discussed with you where you will be standing, so we make sure we get the best shots of you.
I have to stand right here, I gather. And one of the problems is that light's in my eyes, so I can't see the audience, so that makes it a little bit difficult. It's a particular pleasure for me to give the Langbein lecture. I knew Walter Langbein rather well, particularly in the period when I managed the water research program of the USGS. That was close to Walter's heart, and we became quite close during that period. And I must say I knew Walter rather well late in his life. So it's a pleasure for me to give this lecture. Now, one of the things that I learned at the Geological Survey was that one shouldn't speak unless they have something to say. And it seems like a good rule of thumb. And in this audience, that means that this, to me, is a rather academic audience. And the question is, what does one talk about to this academic audience? And of course, having been in research for a number of years, I think I know what makes a good research topic. But I left the Geological Survey in 1994 to do something different, and I've been in business ever since. So I'm a businessman, a consultant and a businessman. And that doesn't lend itself to the kind of academic sort of things that one does. One does some fairly interesting things in consulting, but usually there isn't time to sort of take time to extract the interesting part of it and write it up in the sort of way that you would do doing research. So I haven't done that in 5 years. And I made some suggestions to the committee of things that I thought would be interesting to talk about. They didn't like my suggestions. So after thinking about it, I want to talk about the use of models today. That's something that's reasonably close to my heart, and something that I see not working the way we had hoped, I think, or the models are not being used in the way that I had hoped they would be used when we started in this business some 30 years or so ago. So I want to talk about that. Now, and in doing that, I'll put the first slide on. Oops, I think it went backwards. Okay. Now, my alternative title of this talk was that most groundwater models can be destroyed in court. And what I see is that the models have become too complex, too large, and too expensive. And I think that we as hydrologists are doing ourselves a disservice by the way the modeling business has gone. Now, and I see this particularly in my consulting business. I've looked at and tried to evaluate a number of models in California. In some cases, the modeling has run $500 to $1,000 an acre. You can imagine, we're talking about models that are multi-million-dollar with everything but the kitchen sink put into the modeling. So what happens in those cases is that when we now start to talk to the clients about let's build a model and see how the system behaves, the clients, of course, see dollar signs, large dollar signs, and they shy away, and we don't get the opportunities to use the models in the way in which I think they should have been used, or could have been used at least. And I've tried to ask myself, why has this happened? Why have we gone in this direction? I think there are a number of reasons. One of the reasons is that I think many of the consultants, particularly the better consultants, have gotten involved in litigation. And they've gotten into situations in the courtroom where the models have been challenged by the other side. And in order to avoid those challenges, they go back and look at everything. So everything is examined in detail so that you can stand up in the courtroom and say, well, I looked at that. So when the other side said, well, did you look at this? Yes, I looked at that. I looked at this. I got into an argument recently about a 40-acre bean field, whether it was irrigated or unirrigated in the model. And you know, those kinds of details, it seems to me, we're kidding ourselves about looking at the results of the models under those circumstances. All right. Now, I started to say why I think this has happened. The other thing is that the computers have gotten bigger, so we can solve bigger sets of equations. It's not difficult with the kinds of computers that we got on our desktops today. Also, the sort of pre-processors have come along, particularly for mod flow, pre and post processors, and it's easy now to put in a lot of cells, put in a lot of layers, get the models very large. So those are the things I think that are driving it. Now, what did we start out to use the models for? I can't see that slide very well, I apologize. But the first thing is that the models we're using the models in a way in which to determine who's responsible for certain actions, particularly what PRP contaminated in a certain aquifer. Where did the contamination come from? Who was the PRP? So those are one of the issues that the models are being used for. Another issue is so in this sense, we're trying to backcast with the models, go backward in time, to try to see, who was responsible. Okay, the next thing is we've also tried to predict into the future what happens if a certain stress is put on the system, and a lot of the models do that sort of predicting into the future. When we've gone back to look at how well we do with those predictions, it turns out they're not very good. The sort of post-audits we've done suggest that the predictions were not very valid, for good reasons, I think. Now, some of the things that the models could be used for is to gain a better understanding of the system. And that doesn't take a terribly sophisticated model in most cases. In most cases, we could do that with a relatively small model, fairly unsophisticated, and we could ask simple questions of how does the system behave. I don't see very much of that going on. We could also use the model to try to design where are the appropriate places to sample the system. Where should we be looking for data in the system? That isn't going on very much, in my opinion, either. And the final thing is the models can be used, I think, in a policy analysis to try to say, in a particular case, how is the best way to manage this aquifer? Are there better ways to manage the aquifer? And what drives the aquifer? What are the critical issues as far as the aquifer is concerned in terms of its management policies? All right. So those are my categories of what I think the models are being used for, and I think we're seeing that much of the effort lies up here, particularly at the present time, at least what I see in my consulting practice. And these are the models that I think are getting very complicated. All right. Now, one of the other things that you say to yourself, okay, we're going to go to court with these models. What are the things that we need in the modeling effort? And we all know what those are. We need some estimate of the transmissivity. We need some estimate of the storage coefficient. We need the boundary conditions. We need what the stresses are in the system. Now, the question is, how many of those things do we measure independently? Well, in the case of the pumping tests, we certainly have procedures where we can measure transmissivity by pumping tests and various kinds of pumping tests. All right. Those pumping tests also yield some estimate of the storage coefficient, but usually what you find is that when you extend the model into the future or you try to make some long-term assessment of what the storage coefficient is, what you get from the pumping test analysis is always on the low side, or generally on the low side. So what we see is we don't really know that pumping test, we don't know from the pumping test the storage coefficients very well. And we get a better measure of that from the long-term analysis as a system, usually done with the model. The boundary conditions are assumed by the modeler. Sometimes we have pretty good ideas on where the extent of the model goes or where the extent of the aquifer goes. And then the models are very sensitive to what the stresses are. The stresses are known not all that well. We estimate stresses in many cases from the electric use of metered electricity. Of course, the pumping depends on how efficient the well is, and often we don't know how efficient the well is, so we estimate the pumping based on the electricity, or we estimate the pumping based on, in agricultural situations, what the crop requirements are. So again, we come back and we see that these things, the stresses which are critical to the modeling, are not known all that well. In fact, in some cases, I don't think they're known very well at all. All right, so that's the flow models. So what we come back to is we may be able to measure the transmissivity reasonably well independently of the model. Most of the rest of these, and we may have some reasonable estimate of what the stresses are. When we look at the transport models, we see something a bit different. What we find is, first of all, the estimates of porosity are not very good. There aren't very good ways to measure porosity. Sure, you can measure core analogy. You can measure cores in the laboratories. Cores have the same problems with measuring permeability in the laboratory. So you come back and you see, well, we make an estimate of porosity based on what the aquifer material is. We don't, rarely do we go in the field and try to measure the permeability, measure the porosity with some kind of neutron probe. It's done, but rarely. Okay. We find from the dispersivity that we don't know what the dispersivity is. We know it grows over this, usually with the distance that the contaminant is moved, it is very rarely measured independently. So we were coming back to, and we go on, the sources particularly are rarely known in time, particularly when you go back and you say to yourself, well, when did that contaminant come into the system? We don't know. We know the plant was built in 1962. We have some idea of what the contamination looks like at the moment. We don't know what that source term looked like. So, and the same is true of the chemical reactions. How do we get the chemical reactions? Well, we get the sorption from, in fact, we get most of these parameters from the model fit. So you come back and you say to yourself, these things are not measured independently. We're getting them from the models. And then you say, well, how good are they? And I think, well, it comes back to how you feel about the inverse problem, and how good is your optimization on what the parameter set should be. But again, you're backing this, almost this entire parameter set out of the transport models. They're not measured. So for that reason, you can come back in a courtroom and challenge most of these things. So, you know, you can say, well, did you measure that independently? No, we got that out of the model, which may or may not be adequate. All right. Now, what I'd like to do is show you a model analysis that we did recently for Mexico. I'm working for the World Bank in Mexico, and this Hermosillo aquifer that I'm going to show you in a minute is kind of a case study of aquifer problems in parts of Mexico. And I'd like to use it to illustrate how I think the models can be used in an efficient way. All right. Now, as I said, I'm working for the World Bank. We're looking at groundwater all over Mexico, but we're focused in on Hermosillo as one of 5 aquifers that we're going to try to use as kind of case studies. I'm working with an economist, an old-time friend, Bob Young, from CSU, retired from CSU. Bob and I worked at Resources for the Future in the early 1970s on similar problems. And this aquifer is rather interesting. Pat Domenico did a model of this some 25 years ago, so Marty Mifflin tells me, as part of a water plan for Mexico. So it's an aquifer that's well known. It's an area of groundwater development in Mexico that's well known. It's near Hermosillo in the state of Sonora. And as you can see here, the aquifer started to be developed in about 1945, and we've got development right up to the present. It peaked here, and I can't see that very well, but I think that's 1960, somewhere in this range. And you can also see that the Mexicans did change their method of measurement here sometime around 1980, and these are estimates here, as you can see. They changed from the measurements in here where we get sort of detail to something that looks like it's estimated over some period of time. All right. Now, the problem here is seawater intrusion. That's what I was told when we started on this project. And as you'll see, as we get to the end, it is the problem. But but I went to Mexico at Christmas time to look at this aquifer, to look at the development of the aquifer at Hermosillo, camping actually, an interesting experience. But, and what I expected was that near the coastline there would be, you know, the sort of thing that you see with seawater intrusion, everything would have gone out of production. What we saw was that it had gone out of production along the coastline, but it was out of production everywhere. There was a lot of this irrigated area that had been let go fallow. So it was clear that the only problem, not the only problem was seawater intrusion, something else was going on as well. All right. Now, I apologize for this. This is from a Mexican report, and I apologize it's not very legible. This is a 100-kilometer by 100-kilometer grid on here. This is the Gulf of California. The city of Hermosillo is right here. This is the Hermosillo coastal plain. It's a rather featureless plain for the most part. Guaymas is here, and another community of Quino Bay is here, Baja Quino. I can't say it right. Anyway, this happens to be the water table. Well, let me back up a little bit. The aquifer here, the principal aquifer, is about 200 meters thick, and it's an alluvial aquifer. You realize that the Gulf of California here is very active tectonically, so this is a very recent aquifer, and it's highly permeable. And there's a development in here, and the water table here is 55 meters below sea level. So we've got a cone of depression that sits right in here that has water levels 55 meters below sea level. And that's about 30 kilometers or 35 kilometers in from the Gulf of California. This happens to be a map of concentrations of total dissolved solids in this case. And I apologize again, you can't see much, but what you see in here is this is the area that's contaminated, and I'm sure you can't read that, but there are things in here of 3, 4, 5,000 parts per million total dissolved solids, and it's in from the coast about 15 kilometers or so. 10 kilometers, all right. Okay. And so we put together a model of this area, including the seawater intrusion. This is the model grid, as you see here. It's not terribly large, 50 by 50. This area in here is the irrigated area. So there's an irrigation area here, and there's some irrigation right up in here. But you want to keep this area kind of in mind here. This is where the principal portion of the irrigation is, not very far in from the coast. All right. So we modeled it, first of all, to get some kind of 1996 drawdown. And this is the model here showing we get about 55 meters of drawdown. It doesn't have all the features of the observed drawdown, but it isn't too bad in terms of fitting the cone of depression over the entire area. So that's the 1996 water level projected by the model. This is the seawater intrusion projected by the model, and you see that there's a zone here of this goes from zero. It shouldn't be zero. It's about 300 parts per million background. But anyway, this is the buildup from seawater coming in, and we go from something like 500 here to around 5,000 in this area. And you can see the bay here, this Quino Bay, has some big effect on it. At the moment, 1990s, present time, we've lost about 12 to 13% of the irrigated area. So you can see this was the original irrigated area right in here, and something like 12% of it has been lost to seawater. All right. Now, one of the things we tried to do in this case was to link a simple economic model to the groundwater model. So we calculated what the water pumping would cost in terms of the lift costs. We calculated both the fixed costs in terms of the investment costs and the pumping costs associated with water development. And then we looked at this set of crops, which was determined by the Mexicans here. You can see I think there are 17 or 18 crops here. Some of them are field crops, and some are fruits, grapes in particular, things that are higher value crops and require more care in terms of the irrigation and also some investment in developing the crops themselves. Particularly things like grapes, you've got 3 years or so before you begin to get any yield. There are pecan trees in here which take a longer period of time to get some yield. So this was developed by the Mexicans. Things here are here in hectares, and I don't know if we got prices here in terms of pesos. All right. So in putting together the model, what we put together was a rather simple algorithm saying what we would look at is the costs of pumping, costs of water, then the cost of production, and make a simple decision, could the income from the particular crop cover the cost? If it couldn't cover the cost, we said we're going to eliminate that crop. So it was a relatively simple decision. We couldn't cover the cost of the fixed costs and the water costs for the particular crop. We eliminated it. So from further consideration. All right, so this is one of our first simulations, and what we got here is an income stream, I think. I can't read that over there, but I'm not, yeah, I think this is the income, net income? Net benefit, right. Income, net benefit. And you can see we start out here somewhere around, as I recall, 600 million pesos, and the thing declines over time. There's some difference in the energy costs. The energy costs at the present time are about 0.2 of a peso per kilowatt hour. That's a subsidized cost. The Mexican government is subsidizing energy for agriculture. The real cost is something like 0.6 of a peso per kilowatt. Excuse me? Excuse me? Pesos. They use the dollar sign, but it's pesos. And you can see this is a projected income stream out to something like the middle of the next century. All right. And what happened in this case is that of those 17 crops we started out with, this is what we were left with. So after we eliminated, even in the first year, we eliminated most of the field crops. Most of the field crops are no longer profitable. And that's what we saw in the field. When you went down there and looked, you saw that a lot of the field crops have been dropped out. And what you were left with were basically high-value crops: citrus, pecans, grapes, particularly table grapes. Table grapes turns out to be the crop of most value. All right. This is a projection for 2048, I believe, or 2050. What the water table looks like. It's come up substantially because we've eliminated a lot of the area in the future. In this first simulation, all we did is say, we're going to drop out those things that are no longer profitable. All right, and this is a projection for the saltwater interface. It's again come in quite a bit more. And I'm not sure, I can't read that over this. I think is the total pumping? Yeah. Okay, all right. Now then we said to ourselves, okay, what would happen if we cut this back by 50%? Suppose we cut back the area by 50%. Can we slow down the saltwater interface? Well, the fact is you can slow it down a little. So again, this is the effect of the electric prices. I went over that. All right, and this is what it looks like in terms of how much future. What is our loss to seawater intrusion? So this is a percentage of the area that's lost to seawater intrusion with the first scenario. Okay, so then we cut it back by 50%. And I can't read, that's the pumping? Oh, okay. I mean, it's rather simple. All right, and then what you see is the water level comes up quite a bit. So we've had some benefit in terms of the cone of depression. This is how we drop the income. The income doesn't, we've cut it in half, obviously, so that's what happens. All right, and this is what happens in terms of the seawater interface. This is what we lost in the initial simulation. In other words, we simply cut out the areas that were, and when we cut it in half, we gain a little bit, but it's about 5% here out at the, in terms of what we gain in the area that's lost to seawater intrusion. It's not much. All right. So the next thing we did was to say to ourselves, all right, suppose we take the highest value crop now, and we say, as we eliminate certain crops, let's take that acreage and put it into the highest value crop. The highest value crop turns out to be table grapes. Okay, so that's what we've done in this case, and you can see I think that's pumpage. I can't read it from here, I'm sorry. Anyway, the irrigated land. So it jumps it back up again, and you can see that we irrigate quite a bit more of the area. All right. Now, that's the pumping, and you can see the pumping jumps up as well because we're irrigating much more land as we replace it with table grapes. The big benefit is in the income. You can see here our base case. We had something like, as I recall, 600 million pesos. We jumped that up by 4 times. So we greatly increased the income from the area if everything went to table grapes, the highest value crop. So that's interesting. And it means that we could, by doing this, increase the income from the area very substantially, a factor of 4 in this case. All right, but here's the seawater interface after 50 years, and you can see we really cut into the irrigated area now. So we've got, in fact, the seawater way in, and we've eliminated the bulk of this larger irrigated area. And that shows up here in terms of the percentage of the irrigated area. This is the base case, and now we're up here to about 40 to somewhere around 40% of the entire area has gone to seawater. So we've got a very big problem in terms of seawater intrusion, although the income stream doesn't look so bad. You know, you can say to yourself, okay, that income stream for the next 50 years really doesn't look bad. All right, now this is the income stream from this particular scenario where we replaced everything with table grapes. This is the income stream without the seawater intrusion, and this is what happens when we put the seawater intrusion on here. So you can see that this decline in the income stream is a result of the seawater intrusion. All right. Now, then we did one more scenario, which I thought was maybe the most interesting thing we did. We said, okay, here we sit at 1996, this was the last time we had data. Suppose we just cut the pumping off, stop pumping. What happens to the seawater interface? And what you see is, here we are right here, and we stop the pumping, and here's the seawater interface. And we all know that's going to happen. We got a disturbance that's about 50 years old. It takes about 50 years for that disturbance to die out of the system. But what that means in this case is we're going to continue to have seawater intrusion in this system no matter what we do. So, and it'll about double. We've got it here at 12 to 13%, and it goes to about 25% in the next 50 years. So that's what you'd expect intuitively, but I think it's, you know, it's interesting to do that with a model and say, okay, what really happens? And then a little bit more of the story. All right. Now, so there's some policy relevant decisions to be made here. First of all, you can see that we could run this system for 50 years, get quite a lot of income out of it. And if you said to yourself, well, let's discount that back to present net worth, you know that with any kind of a positive discount rate, you will not see much benefit beyond 50 years. In other words, you're weighing everything to the present, and of course that's a substantial income stream, and you say to yourself, well, you know, those farmers can make a lot of money down there if we just continue the system. On the other hand, if you want to continue this system sort of indefinitely, so you say to yourself, we want some kind of sustainable system here, you can see that you're going to have to do something with the saltwater interface. The saltwater interface is really a problem, a long-term problem for the development of this aquifer. And unless you stop that saltwater interface, you're ultimately going to lose the entire development. So there's it seems to me real policy decisions to be made here. The question is, you know, do we do as we've done in this country, or we say to ourselves, well, let's go ahead with the development. We'll worry about the future after this development is over. And we certainly did this in the water, in the arid parts of this region, of the United States at least. All right. So then you say to yourself, okay, the World Bank said to me, What could we do to stop this? Well, the traditional thing to do, of course, is to come in here along the coast and put in a line of barrier wells, inject in a barrier, and stop the seawater intrusion. And here we are with a barrier that's about 25 to 30% of the total pumping. We're pumping in at 200 million cubic meters a year here, which is about a third of the total withdrawal. And a barrier line right in here, okay? And that's kind of interesting because what you see is we didn't get it quite far enough in, and there's a lobe of seawater here that's beyond the barrier, and it shows up kind of in here too, but it shows up best here. So the barrier in this particular case is not in a very good position. And if you move that barrier, you move it in a little further, of course you can control that seawater interface, and you can hold it. And 200 million cubic meters a year look like it wouldn't stop it, but it would certainly slow it down one heck of a lot. All right, so then you come back and you say to yourself, all right, where are you going to get 200 million cubic meters a year? Well, it's not so easy to get unless you come up here somewhere and pump it out of the aquifer and then pipe it down to the coast. It seemed to me that the other possibility was to put in a line of wells along here and pump out, much as we do with pump and treat systems, try to capture that seawater as it's coming toward you. And this is a simulation of that particular system where we put a line of wells along here and pumped out at 200 million cubic meters a year again. And you can see again that you can control the interface. It doesn't totally stop it. It would have to be larger, the pumping would have to be larger to control the interface, but it certainly slows it down as we did with the pumping. I didn't look to see, how big would it have to be to stop it entirely. All right. Now, this is the kind of model where it seems to me you gain a lot of insight into the system behavior. And in the model itself was not all that, it was relatively simple, I should say, and as I said, I think it provided us with a lot of insight as to what the policy issues were with respect to this Hermosillo aquifer. And this is the kind of thing, it seems to me, that models are ideally suited to do. All right. Now, I just want to come back and again make my point. And my point again is that I think what we're doing is hurting us in that we've made these models so complex, so big, and so costly that the clients are reluctant to allow us to do the modeling. And for that reason, we don't get to these simple kind of models which give us some understanding of how the system behaves. And we particularly, I don't see very many instances where we're trying to use the models in some kind of policy framework. So it seems to me my conclusion I would suggest to you is that we're hurting ourselves in the way we are using the models at the present time. And with that, I'll stop. Thank you. It would certainly help me. I can't see the audience.
Thank you. Questions? John?
Semantic question. You use the word complex. Later on, you use the word sophisticated. Do you distinguish between sophisticated models and complex models?
No, I don't want to make I don't want to make some kind of judgment, John, about what the difference is.
I have a value judgment in that there are situations in which sophistication is warranted, but that I see the word complex in a negative way, so it's sort of the same thing. You can have an overly complex model that doesn't necessarily represent reality. In fact, it's gone along some curve of complexity to the point in which it has no resemblance to reality at all. But something sophisticated can be based on fact and can represent that reality quite well. The issue here is uncertainty. The complex models replace what you don't know about the system with complexity.
I think that's true.
Are the folks in the back hearing the question clearly? Okay, thank you.
I think this problem is not unique to our community. In fact, you read papers by people from the RAND Corporation where they've talked about modeling war games, you know, sort of global war game models, where they've done the same thing. They've gotten more and more complex. The more and more complex they become, presumably to represent reality, but then you lose sight of cause and effect, and you have no way to calibrate the models. I mean, they get so complex that you're really out of the realm of calibration.
Yes, Brett?
I think one of the things that we've done is to mix up modeling that is primarily a research activity with an actual application. In other words, things that should be regarded as research tools are being applied or pushed beyond their capabilities. I mean, gaining knowledge and exploring is one thing. Applying a model in a litigation situation is another. We ought to make distinctions between that, but it seems like we don't.
I'd say that's true, Fred. It seems to me that what you see in the litigation, it seems to me, has pushed the thing more and more complex. And I think my own assessment is it's done that because the modelers want to cover everything. They don't want to be in a position where some counsel for the other side gets up and says, well, did you consider this? And did you look at that data? And so what happens is the models get more and more expensive, more and more complex, and the modelers are trying to cover their rear ends. Well, I mean, you have to ask yourself, why has this occurred? And it seems to me that that's one of the real strong driving forces in what I've seen. I'm sure I haven't answered all the questions.
So what would be your answer if you're asked, have you considered this and have you considered this? I mean, you have to answer something, right?
Well, I don't think it's so bad to say, well, no, we didn't look at that. You know, no, we didn't look at that. And then, you know, at some point, the judge or the jury, if there is a jury, get to the point where the model has been totally disqualified. And I think that, you know, or the modeler has been disqualified, one or the other, and then they discount it. And you know, you're always going to be, when you model something, you're always making assumptions. You're always trying to idealize the system. It isn't the real system. You're idealizing it. You're making assumptions. And you're going to be vulnerable in those assumptions. Or at least the potential is there. Yes?
Yeah, just a comment, John, and that is that it's interesting that you've wed these economic models with these groundwater models, and that points out that as a broad class, modeling and making projections of the future have undergone a retreat. In the 60s and 70s, economists were hired by corporations to make long-term economic forecasts that were based on modeling results, and in the 80s and 90s, that ability to make predictions, economic forecasts on the part of corporations has come into some sort of retreat. And I think what you're seeing across the board, not just in hydrology, but in a wide, broad suite of fields, is a retreat from our ability, or from the public's trust in the ability to make computer-based models that predict the future well. Would you agree with that?
Yes, I would agree with that. But let me come back and talk a little bit more about this modeling in Hermosillo. The point of the modeling in Hermosillo was not to make some projection into the future. The point was to try to explore different policies and see what the difference in those policies are. Try to give yourself some guidance as to what are the policies that might be of interest in developing the future of that aquifer. And I think you can see there, again, I'd like to come back and say, one of the questions there is, you know, if you did that in a traditional economic sense, you can see that the thing has some value over the next 50 years. And certainly you would, if you discounted that back to some present value, you'd say, oh, there's a lot of value here. If, on the other hand, you say to yourself, well, we want to sustain this thing, then you've got a problem. The development is not consistent with the seawater intrusion, so unless you do something to control the seawater intrusion. I think that's the most interesting thing about it. It is not a sustainable development by just continuing to develop, and you can't cut it back by 50% or something of that sort and say to yourself it's going to be sustainable. You can see that you've got 50 years of development. That 50 years of development is going to cause another 50 years of seawater intrusion if you do nothing. Don't pump anymore. So those are the interesting conclusions, and those are not things trying to predict the future. They're trying to say, how is this system functioning, and what does it mean in terms of the policies? Yes.
John, along those lines, it seems to me that what you're arguing for is a kind of scenario analysis to inform policy decisions. Suppose what you want to make a decision on is something related to, for the sake of argument, disposal of radioactive waste. How would you use this kind of scenario analysis to inform a regulatory body?
George, you would do that to me. You open up a whole can of worms. Let me say this. I think one of the things that, you know, we say to ourselves, well, the models in the nuclear business, I think in particular, are, you know, we're trying to make projections out of 10,000, maybe 100,000 years, maybe 1,000,000 years. Now, I don't think any of us think that the models are good enough to do that. I mean, I'm getting myself in a bind here, George. You know, there's this whole business of validation. Did we calibrate the model? Certainly we can't calibrate the model for those periods. The questions, I think, come back to, do we understand these processes well enough to be able to make those kind of predictions into the future? Are the processes themselves known well enough? Do we understand the processes? Those are the good issues, it seems to me.
It seems like all models have some uncertainty associated with their predictions, but you didn't talk about the communicating that uncertainty to the decision makers. Should that be part of the modeling process?
Yes, I think it should be. I think it should be. Excuse me?
What's the best way to do that, to communicate it to people who aren't familiar with scientific?
Well, I think one of the things that we did in the past when when the computers were not big enough, we made a single valued prediction into the future. I think that was one of the things that got us into trouble. We had this single valued prediction. We made no confidence limits around that prediction. We all knew it was kind of a best judgment of where we were going. I think we were limited by the computer capacity. Certainly there are ways now to come back and put confidence limits around those things and do it somewhat rigorously. I think we should be doing that.
Value in policy, though, for instance, for Yucca Mountain, to say, is dilution or not much dilution, should we count on it? We can't count on it, therefore let's put our money in engineered barriers or other parts of the natural system. You could get some value out of that if you're pushing your policy concern. But I mean, how aggressive would you be in remodeling Yucca Mountain problem on a regional groundwater flow point of view? I mean, there's a lot of missing data, a lot of gaps in there, but you know, here it's going to come up for licensing one of these days, and you're going to have somebody's got to defend that.
Well, I was just upstairs at the Yucca Mountain policy discussion. I think Rod Ewing made important points about, you know, how do we look at this, particularly in terms of the geologic time frame in which we're operating. Probabilistic risk analysis is, I question that that's the way to go, I think, which was what Rod's point of view. I didn't answer that very well, I'm sorry. Yeah.
John, in light of what you said, what do you see as the major research direction for groundwater hydrologists?
That's a bad question to ask me, Mary. I haven't been thinking about research in groundwater hydrology. I've been doing business for 5 years, so I haven't thought about what is a major research topic. Let me come back and say to you, in terms of the transport modeling, there are large uncertainties in terms of what are the reaction rates. I mean, we stick reaction rates in there. Based on
Something bigger overall. A lot of groups are looking for a theme, a grand challenge. What as a groundwater modeler, can you identify what would be the grand challenge for groundwater modelers?
I don't have an answer, Mary. My crystal ball isn't that good.
John?
Yeah, you were just commenting on the Yucca Mountain session.
A little louder, John.
Yeah, you were just commenting on the Yucca Mountain session and the discussion or the presentation been made about probabilistic risk assessment and perhaps the need for some other approach. Yet a few minutes ago, in commenting on what we should do with models to improve our assessment of uncertainty, you basically said we should do probabilistic risk assessment. So,
I don't think that's what I said, John. I said,
put bounds on things.
yeah, I would say we should try to put some bounds on things. I don't think that's a probabilistic risk assessment in the way we're using performance assessment and so forth to evaluate whether we're going to put waste at Yucca Mountain or at WIP. That doesn't seem to me. I mean, when you start linking model with model with model with model in the performance assessment, it's a much more complicated issue than I think what I was being asked is, suppose we make some projection of water level into the future, should we put some confidence bounds on that? And I think we should. I mean, a single value projection isn't all that good.
Yeah, in terms of the future of hydrology, do you think that some of the costs that are now being put into groundwater models might be better served in finding more accurate ways of determining some of the parameters that you were discussing that were back calculated through inverse modeling?
Well, let me try to answer that this way. I've been involved in a situation in California where there was a lot of money spent on several models. Things of the order of $500 to $1,000 an acre. We're talking multi-million-dollar models. If we had taken, then the questions being asked, if we had taken a fraction of that money and actually collected data, we could have made decisions based on empirical data rather than on the models. And for some reason, there's a reluctance in the reluctance in the community to put money into the basic data collection, and particularly when it continues on, and a not reluctance to put a lot of money into the models. And the models in this case, I think, are way too expensive. And the data collection would have been simple. Some of these things that have to do with what is the stream. When you go looking for water quality of streams, you find the data is really not there. What is it? And this happened to be associated with a stream, and the question is what the water quality was. What was it doing to a particular city's water quality? But if one had spent the amount of money that was spent by putting a continuous conductance monitor in the streams, we would add a lot more information. So it seems to me that in a lot of these cases, one ought to be thinking about how do we collect more appropriate basic data. Yes?
You have recently answered Mary Anderson's question by making that statement. It is the data-driven need of the field, whether groundwater, surface water, where the field needs to go.
Surface water quality, there is a real lack of data. I mean, it's just really not there. We got all this flow data every day, and then you start looking at, well, what was the quality? And we don't have it.
I work for an environmental consulting firm, and one of the constraints, one of the limitations is the fact that we are working with a limited data set for financial reasons, for time constraints, for various different reasons. You don't have the resources to collect, all the conductivity data that you want or whatever, all those parameters that you have a fixed data set. So one of the current practices that I think consultants do is we get around that by putting our best guess for the various parameters with whatever data we have, putting in, literature sources and the best engineering judgments that we have, and then putting that into the model and really trying to achieve a thorough calibration process so that you don't know the parameters explicitly, but you have a set of parameters and a physically based model, a model that gets you a full calibration of your system. And then if you're fortunate enough to have more data, you can perform a validation of that model on a separate data set. You go through that sort of consulting modeling process to achieve a system that best represents, your area. I was wondering what your opinion was on the validity of such an approach, because that's really what you see happening in the consulting world a lot.
Well, let me try to answer that this way. First of all, I have problems with the idea of validation, but that's another issue. What's done in the petroleum industry is that you say to yourself, okay, we got a reservoir out here. We know we don't understand it fully, but we're going to do a model of that reservoir, and we're going to do a history match for whatever period of time we got and get the best set of parameters we have. Then the next thing is we say to ourselves, okay, that's the best tool we got. We'll use it to predict the future, how the reservoir is going to behave. We're very careful in that situation to extend that prediction very far beyond the period of time we've got for calibration. So in other words, if you say to yourself, well, we got 10 years of history for calibration, we'd be very reluctant to project the reservoir behavior much beyond 10 years into the future with any degree of confidence. And it seems to me that's the same business we're in the consulting world, is you do the best you can with what you've got. I do that, and I'm sure you guys do that. That's what we got, that's what we use. But that's not to say we couldn't have spent that money better by doing some better data collection.
You once said that groundwater models cannot be validated. What if they still, in the future, the question is, will we ever be able to validate? And if we can't, what do we do about that?
Wait now. The question of validation comes back to the whole question of validation in science, and particularly where do you come from in your philosophy of science? Do you believe that validation is possible in science? Now, and it seems to me that I happen to believe that Popper was right in saying that nothing can be validated; it can only be invalidated. So from a deeply philosophical viewpoint, I don't think you can say to yourself that you're going to validate any model. Now you can say to yourself, well, we did a pretty good calibration, and it fits the history pretty well, and that's a pretty good tool to extend ourselves into the future, best tool we got. I don't have problems with that. But if you say to me, well, the difficulty with the validation argument, in my judgment, is that we come back and we say in the nuclear business, where we make these projections for 1,000 years, we got a validated model. Now what does that mean to John Doe public? It means somehow we've put quotations around on it that this model is valid. I just don't believe that that's where we are in this business. And I don't think we'll ever be there. And that comes back to my philosophy of science. And I think that's where you got to start with this. It's not an issue and you can make up some kind of rules for validation that don't have to do with what the world believes. But the public out there, when you say validation, they have some idea what that means. And it may not be what you decided it was for your little discipline, but when you go out there and you start selling nuclear repositories based on validated models, that's when I start having problems.
John, we thank you very much for a very interesting talk. I was thinking about in hydrology, if we had this lecture expanded to a few hours and had somebody to talk also about the use of surface water models use of hydrochemical models, if the message would be any different or not. I think the common thing here is water and the question of complexity versus simple models and models that do get applied in practice vis-a-vis what is developed in academia and various research institutions. That question is always with us and will remain with us. And I think Mary's question was very relevant here in terms of what are the grand challenges, particularly as we are moving towards hopefully a new agenda for hydrologic sciences in the future, as agencies are now thinking that finally hydrology is important. Hopefully they will try to seek federal funding for more research in this area. Input in this area is going to be crucial, such as the ones that John gave here. I think this interface between policy relevant science is going to be with us, and more is going to drive how we do science in the future. We appreciate that very much, John, and now that the job is done, you get your official certificate from the section, which is a recognition that you were the 1999 Langbein lecturer. And
thank you, sir. Thank you. Thank you.
Thank you. So before we close, you know that today is a day filled with a lot of actions for the hydrology section. Next is, of course, the hydrology business luncheon, which is in Marriott, Salon F, if they haven't changed the room on us. And I hope most of you have gotten your tickets ahead of time, and because the tickets are apparently sold out, but that doesn't mean that you cannot get them at the door if people don't show up. So we encourage you to come there and have a pleasant meeting. Thank you.
So there's people who make up this